Welcome to this problem walkthrough. Today, we'll be tackling an interesting and widely used problem in coding interviews, problem number 48, rotate image. In this session, we'll break down the problem, explore potential approaches, and guide you step by step towards an efficient solution. Let's dive in. In this problem, you are given a square 2D matrix, which represents an image, and your task is to rotate this matrix 90 degrees clockwise. The key requirement is that the rotation must be done in place, meaning you cannot use an additional matrix to perform the transformation. Instead, you need to directly modify the input matrix itself. The input format consists of an n by n integer matrix, where n is the number of rows and columns. For the output, there isn't an explicit return value. Instead, the input matrix should be updated directly to reflect the rotated version. Let's look at an example to understand this better. Suppose the input matrix is a 3 by 3 grid as shown. The first row contains the numbers 1, 2, and 3, the second row has 4, 5, and 6, and the third row has 7, 8, and 9. After rotating this matrix 90 degrees clockwise, the first row of the original matrix becomes the last column of the rotated matrix, so 1, 2, 3 turns into 7, 4, 1. Similarly, the second row, 4, 5, 6, becomes the middle column, 8, 5, 2, and the last row, 7, 8, 9, becomes the first column, 9, 6, 3. This transformation demonstrates how each row is mapped to a column during rotation. Now, consider another example with a larger 4 by 4 matrix. The input matrix contains rows like 5, 1, 9, 11, and 2, 4, 8, 10. After rotating this matrix 90 degrees clockwise, the rows are transformed into columns. For instance, the last row of the original matrix, 15, 14, 12, 16, becomes the first column of the rotated matrix, 15, 13, 2, 5. Similarly, the other rows transform into their corresponding columns in the rotated matrix. This pattern of rows becoming columns is consistent regardless of the matrix size. For the next example, we see a special case, a 1 by 1 matrix. Here, the input matrix consists of a single element, 1. When this matrix is rotated 90 degrees clockwise, it remains unchanged as 1. This is because there's only one element, so there's no room for rotation. This highlights an important edge case where the matrix size is at its minimum. Finally, it's important to note that the rotation process applies to all elements of the matrix, regardless of whether they are positive or negative. For example, negative numbers are treated just like positive numbers and follow the same rules for rotation. Additionally, the constraints ensure that the matrix will always be square, with sizes ranging from 1 by 1 to 20 by 20, and all values will fall within the range of -1000 to 1000. These constraints ensure that the solution must handle both small and large matrices, as well as a mix of positive and negative values, accurately. To begin solving the problem of rotating a matrix, one of the most intuitive methods is the brute force approach. The idea here is to create an entirely new matrix of the same size as the input and use the observed rotation pattern to populate it. Specifically, we know that any element at position I, j, in the original matrix will move to position j, n1i, in the rotated matrix, where n is the size of the matrix. Using this insight, the process involves 3 steps. First, creating the new matrix, then iterating through all elements of the original matrix and placing them in this new matrix at their rotated positions, and finally, copying the contents of the new matrix back to the original one. While this approach is simple and straightforward, it has significant trade-offs. It requires additional memory to store the new matrix, which results in a space complexity of n squared. This violates the problem's requirement for an in-place solution, making the brute force approach unsuitable despite its ease of implementation. To overcome the limitations of the brute force approach, we can opt for an optimized method that performs the rotation in place, avoiding the need for extra memory. This method leverages 2 key operations, transposing the matrix and then reversing each row. First, transposing the matrix involves converting rows into columns. For this, every element at position I, j, is swapped with the element at position j, I, but only for indices where I less than j to avoid redundant swaps. Once transposed, the matrix still doesn't appear rotated. However, reversing each row achieves the necessary alignment for a 90-degree clockwise rotation. This process is efficient and adheres to the in-place requirement. The transpose operation fixes the diagonal elements and swaps rows with columns, while reversing rows completes the transformation, making this approach both space-efficient and easier to manage than alternatives. When analyzing the complexity of the transpose and reverse approach, we observe that both the transpose and reverse operations iterate through all elements of the matrix once, resulting in a time complexity of O(n squared). The space complexity, however, is O(1), because no additional memory is used beyond the original matrix. This method strikes a balance between efficiency and simplicity, but for completeness, we should also consider an alternative, the layer-by-layer approach. In this method, the matrix is visualized as being made up of concentric layers, and the rotation is performed by moving groups of 4 elements, one from each side of the layer, in a circular manner. For a matrix of size nxn, there are n//2 layers, and each layer's elements are processed independently. While this approach is also in place and efficient, it requires carefully managing multi-step swaps, which can make it more error-prone compared to the transpose and reverse strategy. The layer-by-layer rotation method, like the transpose and reverse approach, processes all elements of the matrix once, resulting in a time complexity of O(n squared). Its space complexity is also O(1), since it operates directly on the input matrix without requiring extra memory. However, it has notable trade-offs. While it directly rotates the matrix without intermediate transformations, it involves a more complex implementation. Managing the multi-step swaps for each layer, especially when dealing with the inner layers, can make the code harder to write, debug, and maintain. With these considerations in mind, the transpose and reverse method emerges as the preferred choice. It is simpler to implement, avoids the pitfalls of manual swaps, and meets all problem constraints, making it an efficient and practical solution. The layer-by-layer method, though efficient, is not the ideal choice due to its complexity and susceptibility to errors during manual swaps across multiple layers. By contrast, the transpose and reverse approach provides a cleaner and more straightforward implementation. It requires fewer steps to achieve the desired rotation and is easier to debug, making it less error-prone. Additionally, it adheres to the in-place constraint without the need for extra memory, unlike the brute force approach. Given its balance of simplicity, efficiency, and compliance with problem requirements, the transpose and reverse method is the optimal strategy for solving this problem. This decision ensures the solution is both practical to implement and efficient in execution, addressing all aspects of the problem effectively. To solve the problem of rotating a matrix 90 degrees clockwise, we first need to understand the pattern of rotation. Each element in the matrix moves to a new position based on a predictable rule. Specifically, an element located at position I, J, in an nxn matrix will move to position J, n1I, in the rotated matrix. This mapping is key to determining how the elements shift during the rotation. To implement this, we begin by initializing a new matrix of the same size as the original. This ensures that we don't overwrite the original data as we calculate the new positions. For example, if the input matrix is a 3x3 grid with values from 1 to 9, the new matrix starts as a blank slate filled with zeros, ready to receive the rotated values. Now that we understand the rotation pattern and have initialized a new matrix, we move on to populating it. This involves iterating over every element in the original matrix using nested loops. The outer loop goes through each row, while the inner loop goes through each column. For each element located at I, J, in the original matrix, we calculate its new position in the rotated matrix as J, n1I. We then assign the value from the original position to this new position. For example, the value 1 from position 0, 0 moves to 0, 2, the value 2 from 0, 1 moves to 1, 2, and 3 from 0, 2 moves to 2, 2. This process is repeated for all elements until the new matrix is fully populated. If required, this new matrix can then be copied back into the original matrix for an in-place transformation. The mapping logic, where I, J, is transformed into J, N1I, is the foundation of this algorithm. Once this is clear, the rest of the steps follow naturally. In terms of complexity, the approach involves creating a separate matrix to store the rotated values, which uses n squared additional space. Additionally, since we iterate through all n-2 elements exactly once, the time complexity is also n squared. The algorithm primarily works with two data structures, the input matrix, which holds the original values, and the new matrix, which stores the rotated version. There are also specific edge cases to handle. For instance, if the input matrix is empty, we simply return an empty matrix. For a single element matrix, no rotation is needed as it remains unchanged. Note that this algorithm assumes the matrix is square. If it's not, the rotation logic would need adjustments. To better understand how this works, let's walk through an example. Suppose the input matrix is a 3x3 grid with values from 1 to 9. The element 1 at position 0, 0 moves to position 0, 2 in the rotated matrix. Similarly, 2 at 0, 1 moves to 1, 2, and 3 at 0, 2 moves to 2, 2. Following this pattern for all elements, the resulting matrix becomes a rotation where rows are transformed into columns. The final rotated matrix is 7, 4, 1 in the first row, 8, 5, 2 in the second row, and 9, 6, 3 in the third row. While this process uses a temporary matrix, optimizations can reduce the space complexity by modifying the matrix directly, which we'll explore further. To optimize the algorithm and perform the rotation in place, we can avoid using a separate matrix by rotating elements along layers. Think of the matrix as having concentric layers, starting from the outermost layer and working inward. By swapping elements between the top row, the right column, the bottom row, and the left column, we can achieve the rotation without needing extra space. Another in-place approach involves diagonal transposition followed by row reversal. First, transpose the matrix by flipping elements across its diagonal. Then, reverse the elements in each row to complete the 90-degree rotation. Both methods eliminate the need for a temporary matrix, reducing the space complexity to 1. This implementation rotates a given nxn2D matrix 90 degrees clockwise in place, as required by the problem constraints. Let's break down the code step by step. First, the rotate function takes the matrix as input. The variable n stores the size of the matrix, number of rows or columns. Step 1, transpose the matrix. The first loop transposes the matrix. Transposing involves swapping the rows with the columns. For each element at position I, J, where J greater than I, the program swaps it with the element at position J, I. This is achieved using the nested loop structure. The outer loop iterates over each row I, and the inner loop iterates over the columns J starting from I+1 to avoid redundant swaps and diagonal elements. After this step, the rows and columns are interchanged. Step 2, reverse each row. The second loop reverses each row of the matrix. This step is necessary because a 90-degree clockwise rotation is equivalent to a transpose followed by reversing each row. The reverse method is applied to each row, which modifies the list in place. The combination of these two steps ensures that the matrix is rotated correctly in n squared, time complexity, and 1, space complexity, meeting the problem's constraints. This approach is both efficient and elegant, leveraging in-place operations to avoid additional memory usage. Here, we are implementing the solution to rotate a 2D matrix by 90 degrees clockwise. First, we define the method rotate that takes a 2D integer array matrix as input. The variable n holds the size of the matrix since it's always square. The process begins with transposing the matrix, which means swapping rows with columns. To achieve this, we use a nested for loop. The outer loop iterates through each row index I, while the inner loop starts at I+1 to ensure we only swap elements above the diagonal. Inside the loop, we swap matrix I, j with matrix j, I using a temporary variable. This step effectively mirrors the matrix along its main diagonal. After transposing, the next step will complete the rotation by reversing the order of elements in each row, as you'll see shortly. To reverse each row, we create a helper method called reverseRow, which takes a single row as input. Inside this method, 2 pointers, left and right, are used to iterate from the beginning and end of the row toward the center. Using a temporary variable, the elements at these 2 positions are swapped, and the pointers are moved closer to each other. This process continues until all elements in the row are reversed. Finally, the reverseRow method is called for each row in the matrix using a simple for loop in the rotate method. Together, the transposing and reversing steps transform the original matrix into its 90-degree clockwise rotated version. Here, we're looking at a 3x3 matrix as our input example. To rotate this matrix 90 degrees clockwise, the first step is to transpose it. Transposing means swapping the element at position matrix I, j with the one at matrix j, I, but only for indices where I is less than j. The initial matrix is shown, and we'll start applying these swaps systematically. After transposing, we begin swapping specific elements. First, matrix 0, 1 is swapped with matrix 1, 0, which exchanges 2 with 4. Next, matrix 0, 2 is swapped with matrix 2, 0, swapping 3 with 7. Finally, matrix 1, 2 is swapped with matrix 2, 1, so 6 and 8 are exchanged. After completing these swaps, the matrix is transposed, and we see the intermediate result. Now, we move to the second step, where we reverse each row of the transposed matrix. For row 0, 1, 4, 7 becomes 7, 4, 1. Similarly, row 1, 2, 5, 8 changes to 8, 5, 2, and row 2, 3, 6, 9 becomes 9, 6, 3. The final result of the 3x3 matrix after performing the transpose and reverse steps is shown here. You can see that the matrix has been successfully rotated 90 degrees clockwise. Now, let's move on to a larger example, this time with a 4x4 matrix as the input. This larger matrix will allow us to apply the same steps and see how the process scales for bigger dimensions. We start again with transposing the matrix. The rule remains the same, swap matrix I, j with matrix j, I for all I less than j. Looking at the swaps, matrix 0, 1 is swapped with matrix 1, 0, exchanging 1 and 2. Then, matrix 0, 2 is swapped with matrix 2, 0, swapping 9 and 13. Next, matrix 0, 3 is swapped with matrix 3, 0, exchanging 11 and 15. This process is repeated for indices where I equals 1 and 2, completing the transpose. The intermediate result shows the matrix after all these swaps, with rows converted into columns. Following the transpose, we now reverse each row to achieve the rotation. For the first row, 5, 2, 13, 15 becomes 15, 13, 2, 5. In the second row, 1, 4, 3, 14 is reversed to 14, 3, 4, 1. Row 3, 9, 8, 6, 12 becomes 12, 6, 8, 9, and the last row, 11, 10, 7, 16 is reversed to 16, 7, 10, 11. The final matrix after reversing all rows is displayed, and just like the 3x3 example, the 4x4 matrix has been rotated 90 degrees clockwise. Here's a smaller example with a 2x2 matrix to further simplify the process. The initial matrix is provided, and the first step is to transpose it. Since this is a 2x2 matrix, there's only one swap needed. Matrix 0, 1 and matrix 1, 0 are exchanged, which swaps 2 with 3. At this point, the matrix is transposed. With the matrix transposed, we move on to reversing each row. For the first row, 1, 3 is reversed to 3, 1. Similarly, the second row, 2, 4 is reversed to 4, 2. The final result shows the matrix rotated 90 degrees clockwise. Even with smaller dimensions, the same two-step process applies effectively. To summarize, rotating a matrix 90 degrees clockwise requires two main steps. First, transpose the matrix by swapping elements across its diagonal, turning rows into columns. Second, reverse each row to complete the rotation. This approach works in place, meaning no additional space is needed beyond the input matrix itself. By following these steps, you can efficiently rotate any square matrix. To analyze the time complexity of our solution, we break it down into two main steps, transposing the matrix and reversing each row. First, transposing the matrix involves swapping elements across the diagonal, where matrix I, J is swapped with matrix J, I, but only for indices where I is less than J. This limits us to the upper triangular part of the matrix, excluding the diagonal. The total number of swaps corresponds to the sum of the first n1 integers, which is calculated as n times n1 divided by 2. Since each swap operation is constant time, the overall time complexity for transposing is O, n squared. Now, for reversing rows, each row of size n takes O, n, time to reverse, and with n rows in total, the combined time for this step becomes O, n, multiplied by O, n, which is also O, n squared. When we combine these two steps, the time complexity of the entire algorithm remains O, n squared. Now let's evaluate the space complexity. This algorithm operates directly on the input matrix, modifying it in place without allocating any additional data structures. The only extra space used is for loop variables, such as I and j, which require constant memory. As a result, the space complexity is O, 1. Additionally, the time complexity is consistent across all cases, whether best, average, or worst, because it depends purely on the size of the matrix and not the specific values within it. This means the time complexity is O, n squared, regardless of the input, and the space complexity also holds steady at O, 1, in all scenarios. Finally, let's compare this approach to a brute force method. A naive solution might involve creating a new matrix and manually placing each element from the original matrix into its rotated position, which would require iterating over all n squared elements. While the time complexity for this approach is still O, n squared, it incurs an additional space complexity of O, n squared, due to the extra matrix. In contrast, our current solution is far more efficient in terms of space, achieving O, 1, space complexity by working in place. Both approaches share the same time complexity of O, n squared, but our method avoids the overhead of creating and managing an additional matrix. Mathematically, we can confirm this efficiency as follows. Transposing involves approximately n times n1 divided by 2 swaps, which is O, n squared, and reversing rows requires O, n, operations per row for n rows, also resulting in O, n squared. Together, these steps yield an overall time complexity of O, n squared, with space complexity minimized to O, 1, due to the in-place operations. When rotating a matrix, one of the most common mistakes is mishandling the indices. For instance, during a 90-degree clockwise rotation, it's easy to confuse which element in the original matrix corresponds to which position in the rotated one. Miscalculating these relationships can result in elements being misplaced, leading to an incorrect final matrix. Another common error is modifying the original matrix too early. Without carefully preserving the values being overwritten, the transformation can lose necessary data, which will cause the solution to fail. Both of these mistakes often show up in edge cases, such as when the matrix is non-square, and it's crucial to avoid these pitfalls by carefully managing indices and understanding the transformation process before making in-place changes. Another frequent assumption is that the matrix will always be square. While many problems explicitly guarantee this, others might include rectangular matrices. Assuming a square shape when the input is not, can cause index errors or even runtime exceptions. Similarly, edge cases like a 1-by-1 matrix or an empty matrix are often neglected during testing. These cases can lead to out-of-bound errors or incorrect outputs if not handled properly. Additionally, inefficient implementations can be problematic. For example, solutions that use unnecessary nested loops or auxiliary matrices might work but are suboptimal. Such approaches can fail time limits in competitive programming or struggle with large inputs. Optimizing for both time and space is essential to ensure a robust and efficient solution. Success in interviews often starts with fully understanding the problem. Make sure you clarify whether the matrix is guaranteed to be square or if variations, such as rectangular matrices, are possible. Check the constraints, such as the allowed operations and whether the rotation must be done in place. Practicing the pattern of index mapping is also critical. For example, knowing that an element at position I, j, moves to j, n1i during a 90-degree clockwise rotation can help you quickly derive the transformations. Furthermore, when the problem specifies constraints like in-place solutions, focus on minimizing auxiliary space. Finally, always test your solution against edge cases, including empty matrices, single rows, or 1-by-1 matrices. Demonstrating thorough testing can leave a strong impression during an interview. Matrix rotation is a foundational concept that connects to several related problems. For instance, LeetCode 48, rotate image, is the classic question requiring an in-place rotation of a square matrix. Another important problem is LeetCode 867, transpose matrix, which focuses on transposing matrices, a key step often used in rotation algorithms. Spiral matrix, LeetCode 54, introduces traversal in a spiral order, which helps build intuition for matrix manipulation. Lastly, search a 2D matrix, LeetCode 74, challenges you to efficiently navigate and handle 2D matrices, testing your ability to work with these data structures in practical scenarios. Exploring these related problems can deepen your understanding and prepare you for variations in matrix-related questions. There are several approaches to solving matrix rotation problems, each with its own trade-offs. The brute force method involves creating a new matrix and copying elements to their new positions based on rotation rules. While straightforward and easy to debug, this approach uses extra space proportional to the matrix size. A more space-efficient method is the in-place layer-by-layer rotation, where elements are swapped in groups of 4, one layer at a time. This optimizes for one space but can be trickier to implement. Another popular approach is the transpose and reverse method, where the matrix is first transposed and then each row is reversed to achieve a 90-degree rotation. It's simpler than the layer-by-layer method but requires 2 passes over the matrix. For advanced scenarios, recursive rotation can also be used, dividing the matrix into smaller submatrices and rotating them recursively. While this is useful for understanding recursion, it's generally less efficient for practical use. Great job reaching the end of this walkthrough. To summarize, we successfully rotated the matrix in place, optimizing for space efficiency. Remember to practice similar problems to enhance your skills in matrix manipulation and in-place algorithms. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!